Hi, my name is Jerome Hugues. I am the PI of the TwinOps project, a one-year exploratory project funded by the SEI during FY20. TwinOps aims to address the challenges in building cyber-physical systems. We note that cyber-physical systems still exhibit misbehaviors after field test. What we observe is that their engineering relies on models built in isolation, limiting in-depth unit and integration testing until the system is done. In this project, we are combining DevOps and model-based engineering to ease the construction and deployment of systems, their simulation test benches, and digital twins. TwinOps combines system models, software models, and physical models to improve system understandings. TwinOps builds on the expertise of my team working on model-based engineering. The MBE team within the SEI improves the state of the art and influences the state of practice to build safety-critical systems faster and with confidence. Our vision is to leverage models to create the best design that will hold up over time as the system evolves. Test the design in all its dimensions, functional, timing, performance, security, or safety, using state-of-the-art technologies as early as possible, even before the software is actually written. This is made possible by defining a high-level modeling language that combines hardware and software concerns and allows to reason on the architecture core quality attributes. To achieve this vision, the SEI has been developing two core technologies to support it. First, the SEI Architecture and Analysis Design Language, or AADL. AADL is a domain-specific modeling language for modeling safety-critical systems, merging both software and hardware concerns and populated with a large set of properties to finely tune the system. This language is supported by many tools, including SEI Hosate toolset that supports model editing and analysis capabilities. Both technologies are increasing in maturity through multiple case studies for the US Army and its partners. We are strong advocates of Modelcentric approaches and of the AADL language, but we do acknowledge that AADL is not the only language when it comes to design cyber-physical system. Let us consider the case of a basic UAV. Its architecture could leverage more precise models for specific engineering steps. For instance, symbolic models that define its control laws. In addition to those models, we may use AADL for the embedded system architectures and define the core attribute of the software prior to implementing it. In addition to that, because we want to build a CPS, we will need a CAD model for the mechanics. Ultimately, all these models are integrated to build the system. However, what we note is that those models are built in isolation, which means that, as part of the integration test, what we may discover is that some specific hazard or threat, for instance considering safety, were not properly captured and mitigated by the AADL level because they come from actual sources from the CAD models that were not available at that time. Indeed, such issues such as sensor timing jitter, bias, imprecise component behaviors in both the functional or safety domains are still discovered late during testing or even after the system has been deployed. Recent incidents like the Boeing 737 MAX MCAS issues or autonomous vehicle incidents have all in common an imprecise characterization of the interface between cyber and physics. This leads to subtle bugs in time-sensitive control, detection and handling of exceptional conditions. Additional sources of truth exist, and actually all those models that have been built exist and participate in this single source of truth of the system. Each of them exhibit more precise behavior or specific misbehavior when it comes to safety that will have a deep impact on the engineering, and those should be considered. And this is exactly one of the key objectives of TwinOps, leveraging all those models so that we can use more precise models instead of naive abstractions when it comes to validation and verification. Ultimately, we want to combine all those models, all those domains, including system engineering, to improve on the engineering of cyber-physical systems. That being said, and before we go into the definition of TwinOps, let us do a technology focus on model-based techniques. Models, generally speaking, are abstractions that address specific concerns. One can say, by analogy to various words, that models are nothing but static and dynamic architectures. A review of modeling techniques reinforces this view with different types of models. For instance, SysML package or block definition diagrams are basic static architecture definition, and they are rather informal in that they convey very little semantics on the actual system. SysML activity or sequence diagrams are defining the behavior of the system at a very high level, yet they are usually not amenable to formal analysis like model checking. On the other hand, languages like AADL, Simulink, Modelica, each in their specific domains, bring sufficient semantics to enable rich analysis, model checking, performance analysis, or simulation. We can go even further and consider what we can do with models. Models are usually considered as a way to document a system or to run some analysis. Actually, we can go much beyond and actually generate code from some variety of models. For instance, one can generate code from models ready to be embedded in the system, for instance from AADL to C, from Simulink to C, and get insights from the system by generating software probes and exercising the generated system. We can also generate code so that we can simulate models and generate simulation code as a mock-up of some system parts. This is possible, for instance, using Modelica or Simulink, so that you can simulate the environment of your system. Finally, by combining those two approaches, we may imagine building digital twins. Digital twins allow us to compare the actual systems and its digital doppelganger that lives in the simulated world. By comparing the two, we may assess the system as it is running and do prognosis or diagnosis on the system. Those various model processing capabilities are at the core of the TwinOps project. And now we can introduce TwinOps step by step. The first aspect of it is that we mentioned that TwinOps relies on DevOps and code generation. However, DevOps is a software engineering process, not really a model-based one. Indeed, DevOps aims to create a virtuous circle for software quality, combining development, V&V, deployment, and monitoring in a unified workflow. DevOps is relying on a specific IT infrastructure, offering source configuration management, continuous integration, continuous deployment, using containers and IT microservices. From those premises, what we can do is define what is mod DevOps. The general intuition behind mod DevOps is to extend DevOps capabilities. Model can enrich development activities by producing requirements developers must implement, but they can also provide evidences that those requirements are sound. For instance, the dimensioning has been correctly performed. And in addition to that, reduce some of the development activities by generating code from models. Similarly, operation or ops activities may provide more precise metrics, for instance on timing or resource consumption, that may inform the next iteration in model construction, improving both the model side and the development side of the system. As we define it, Mod DevOps aims to define a system software cohesion culture, something that is similar to DevOps, by considering also models as central artifacts. Mod DevOps is built on the idea that model-based engineering is a natural extension or complement to software engineering. By providing machine processable models, we can increase automation to improve system V&V through code generation, through analysis, and through automation of those activities. Let us take an example to illustrate Mod DevOps in action, so that ultimately we can define what TwinOps is. Let us consider UAV, which is a canonical cyber-physical system. What can, for instance, first use SysML to capture its core mission, stakeholders and key parameters and architecture. From this model, we can derive a controller and a hardware-software architecture that supports it. The controller could be implemented using Simulink, hardware-software using AADL. Let us note these models complement each other. Simulink will define the computation to be executed, and AADL how those computations are actually executed and how they will use specific sensors or actuators to fulfill the mission. Let us note that each model is first validated in isolation, but they can also be combined so that, for instance, performance analysis of AADL will inform on the controller of whether some performance metrics can be achieved. Finally, a C implementation will be derived and, together with the AADL model, be deployed on the UAV. From that particular aspect, we can actually derive what is nothing but a model-to-code pipeline. We can leverage AADL to C code generation, we can leverage Simulink to C code generation, compile the code and deploy it directly. So, through code generation, we can reduce many manual activities. And basically, here what we are demonstrating is how ModDevOps extends DevOps by using not only software programming language as inputs, but also models. Of course, we can extend this pipeline to execute all type of model analysis prior to allow the code generation process. Now that we have introduced this first process, we can go further. Again, using this UAV as an example, we may complement the set of models we are using. And for instance, in addition to the model of the UAV itself, also add a model of the plant, of the environment that will be the theater operation for the system. For that, we can use Modelica. Modelica is a language for defining precisely the physical components of a system. It supports an acausal, equation-driven way of capturing the mechanical aspects of a system. Modelica supports model simulation and also model compilation compatible with the functional mockup interface standard. The interesting aspect of this functional mockup interface standard, or FMI, is to allow for the direct coupling between all those models. By providing simulation capabilities, we can define all type of pipelines. For instance, co-simulation of the controller in Simulink and of the plant in Modelica, so that we can go further in validating the controller. Those various combinations allows for all type of cross-validation using the variety of models provided. For instance, we can validate the controller in the plant using FMI. We can validate the Simulink model combining the AADL and C code, and we can also perform virtual integration by running a mockup of the system using the environment, using a simulation, of the environment provided by Modelica. Let us illustrate this later scenario. So in the second pipeline, we add new steps. We have the Modelica model that we can compile into an FMU, and we can combine it with the AADL model. From that part, we can execute the previous model to code. This pipeline is actually a variant of the previous pipeline. We can actually have two options for deploying the system. Using the first model to code pipeline, what we'll do is that we'll actually use the device driver code to read from the sensors or act on the propellers. In the second pipeline, what we do actually is that we build a simulation of the system, and instead of using the actual device driver code, what we will do is we will interface the functional mockup unit generated from Modelica to simulate sensor reading or simulate the action of propellers on the environment. The second pipeline allows system engineers to analyze precisely their system as they conceive it, and perform all types of mission validation in a purely simulated and controlled environment by tuning the Modelica model. Here, what we have done is basically define two pipelines. Those pipelines are independent from the model itself, and from that, systems engineers may decide in which order they will execute or evaluate them. You may decide to go directly to code and do some rapid system prototyping and deploy on the target, or you can decide to do many simulation waiting for the actual platform to be ready. Those pipelines are just one of the many combinations that we can perform. Another one is simply to consider that we have those two pipelines and we can automate also the deployment of the software. So here we'll take the source configuration management system, execute the model-to-code pipeline, and use a deployment over the cloud, for instance, Azure IoT directly on the target. This pipeline gives us the opportunity to deploy systems directly from models. And here, basically, what we are doing is executing a continuous integration, continuous deployment system from models directly to deployment on the UAV system. We may also execute the model to simulation pipeline that we have defined before and ultimately create a digital twin of the system. This digital twin is taking advantage of all the models that have been created and will allow us to run the system. By combining those two pipelines, what we achieve is actually a complete closed-loop system engineering process, from model to deployment, from model to simulation, from co-execution of the system and its digital twins, so that we can consolidate many engineering data. Those engineering data can be compared in real time for diagnosis, but they can be also compared after the execution of system, allowing for precise re-engineering step or incremental improvement over the system. Those various capabilities are just one of the few scenarios that we can define around this idea of mod DevOps, pipelines, and digital twins. As we defined it, this mod DevOps and digital twins, or TwinOps as we call it, is extending the general idea of DevOps by defining a model DevOps cycle. First, we will plan for the requirements and properties of system and model the architecture and parts of our system. Then we'll perform virtual integration. That is, basically, we'll perform verification and validation at model level to evaluate the feasibility of implementing the system. Then, we will perform code generation and deployment of the system. This relies on automation capabilities or code generation from model to code and from typical DevOps practices of continuous integration, continuous deployment, and deployment over the cloud. From that, we can either run the system or simulate it, or do the two in parallel, like a digital twin. Finally, when this is done, we can collect data, monitor specific specific attributes of a system that we want to collect, so that ultimately we may analyze them to infer any system updates that will be relevant. From all those facets of the project, what we are delivering through TwinOps is twofold. First, we introduce Mod DevOps as an innovative approach to bridge model-based system engineering and software engineering through DevOps concepts. Mod DevOps pipelines allows for a smooth transitioning from model-level validation and verification to software production using code generation from models. Then, we have presented TwinOps, a specific Mod DevOps instance that equips systems engineers with new analysis capabilities through the careful combination of models artifacts as they are built. TwinOps builds on the SEI expertise in DevOps and model-based engineering, and actually reuses many existing tools and combines them through those Mod DevOps pipelines. Future work will address the precise modeling analytics pipeline to improve the understanding of the system, from the definition of the modeling artifacts to monitor, to the logic to implement them, the actual monitoring and data processing aspects. Thanks for attending this presentation. If you have any questions about this talk, you can contact us at the following address or attend the following Q&A session. Thank you.
Hello everyone again, my name is Ipek and I'm here with my colleagues who just presented, James Ivers and Jerome Hugues. There's a question that I see in the chat that talks about, it asks where the presentations are. At the end of each day, you get links to the presentations, and they will be available at our digital library. The presentations that were going on today are not there yet, but by tomorrow you'll be able to stream that. With that, let's get started with the questions. I see one from Patty. Jerome, I think this is for you. And the question is, what is the average time frame for modeling the environment steps? So since you just presented, let's start with that because it's new and fresh in our audience's mind.
Yeah, sure. Thank you, Ipek, and thank you, Patty, for your question. I guess the question that you're asking is probably related to more generally what is the process you want to enforce. By time frame, I understand that in two different ways. When do you need to model the environment? And I will say at any time where you need that input for one engineering step. Is it for system engineering? Is it for simulation? It's part of your project description. The other question is what type of information do you need to build this environment? And that is related to some general question about mod DevOps, which is what type of inputs or what type of information do you want to get from that? So I will say in terms of time to build this environment, this model of the environment, it is as much time as you want until you achieve a sufficient level of accuracy, a sufficient level of precision, so that this model of the environment is good enough for all the information you want to extract. Should it be for testing, for simulation, but also for dimensioning your system. And so depending on the type of system, you will have to discuss with system engineers, with practitioners to see what type of information this model can provide and when to insert it into your modeling process. It's a very tricky question that relies on a lot of expertise across all domains, not just software, not just system, but also mechanical or physical. So I'm sorry, no definite answer, but really a discussion across all teams.
So thanks, Jerome. Maybe that's, I will follow up with another question kind of related to it, building on top of that. You mentioned that you use Simulink models because there are multiple aspects of different cyber-physical systems that not one model is always fit for. Clearly, you need the combination of these models, but what are some of the challenges lying ahead in terms of being able to use multiple models seamlessly together? And what are some of the efforts that are ongoing either at the SEI or other places that move us forward towards achieving that?
Yes, thanks for the question. It's a very large question, a large topic. I would say the key research challenges, and it means that really in the broadest academic sense, is first off, if you want to combine models, you will need to think about the semantics of this model. Some will have continuous time, some will have discrete time, and how to combine all of that is really a tricky open challenge. So I would say from a pragmatic point of view, I would say the answer is make sure that you use each subset of those modeling languages so that you have a clear understanding of the semantics of them. Time is one issue, and when you consider continuous time or discrete time, you may have instantaneous time, and it's a large topic within the cyber physical system community. And do we work on that directly on the SEI? It's really at the borderline of what we're doing for the Assuring Cyber Physical System Directorate, but it's really part of the key questions that we want to address in the coming years because it's really a large question. We want to combine models because we know that we need that, but now we have to define precisely how to do that safely and with confidence.
Okay. Thank you. And with that, I will move to a topic that is probably relevant to both aspects of this, which is developer acceptance. And I will ask this to both Jerome and James, but I will start with James. Part of the challenge that we see on and on related to these new automation environments is whether developers are accepting the new automation and new features, and whether they're able to actually trust the results, both from a perspective of the outcomes as well as the recommendations that go along the way. So, James, let's start with you. What are some of the steps that we can take so that the developers can, in fact, accept the recommendations driven, as well as the new approaches? And Jerome, I will come back to you after James answers, because I think there's a relevant aspect of the model-based engineering aspects as well.
Sure. So I think the starting point for me is to recognize that for a developer to accept a result from a tool, there's at least two kinds of questions they're typically interested in. One is the answer correct? And the other is, does the answer qualitatively match the direction they're looking for? And, right? And to make that concrete, in the refactoring research that we're doing, there are lots of correct answers that will reduce coupling in a system and isolate a piece of software. But they differ in their qualities, much the way different architectures differ with respect to different quality attributes, right? One might be a lower latency solution, another might be more maintainable solution. And so when we look for developer acceptance of these recommendations, we have to understand their preferences and ideally give them some feedback mechanism to help tune the answer. On the correctness side, however, we take more of an approach of making the solution very visible, very auditable, right? By telling the developer step by step, here's the things that are happening, so they can independently look and examine the semantics and not just have to blindly trust the tool because we're changing code without them, but to have that transparency to see what's happening and be able to ask questions and think through in a granular step themselves to confirm that they're okay with that answer. So to some extent, exposing transparently the correctness side of things, preferably in a granular way that's easy to digest, but also taking into account the varying preferences that we know developers have and finding ways to accommodate that in different contexts.
Thank you. And that also goes into how can I actually link the recommendations into end-to-end aspects of the downstream as well as upstream activities. I think the same applies to model-based engineering related approaches. Jerome, what are some of the challenges lying ahead and what are some of the steps that to take so that developers are comfortable with embracing model-based software engineering approaches, as well as some of the combination of modeling techniques that are out there that are available and upcoming?
Yeah, so I would say model-based is a big shift in terms of systems engineering. Should it be software or system engineering as a whole? One aspect is that you are turning all type of documents, all type of knowledge into a collection of models. So the first question usually through that is, first of all, is my model accurate enough for my objective? And so that's a really critical part because in the previous time when people were designing their system, it was a human activity with a lot of discussion, and so there were a common understanding. But now we are transferring this understanding into a model so that a tool can process it. And so the first key question is my model complete enough for a specific design objective? And it's not really an easy question. There is a lot of issues behind that. We discuss semantics, but it's also a regular concern in software engineering. I mean, there is still this joke about when do you stop requirement engineering and when do you start architecting your system? And it is still an open question. The second one related to validation or verification or model processing is what type of feedback do you get? So James explained already this idea of explainability of the results that you get through automation. And so for me, it is really asking the question of what does it mean to do IV and V, independent validation and verification. For some systems, a safety critical system, you really want to have a split between the people who design and the people who do the IV and V. When you interact with the MBE tool, you are really in that particular situation where some of the engineering, for instance, when you perform code generation, is done by a black box. You send requirements, which are basically your model, and you get a software. And so the question is how to do this type of IV and V, where instead of humans, instead of subcontractors, you have a machine. And it is asking a very interesting question in terms of how to interact. And again, it's really a fascinating research challenge because we know that we need automation, but now we need to trust that automation. Whether that automation is provided by AI or not is not even the question. It's how to trust automation as a general philosophy when we design our systems.
And that's actually where both of these pieces of work, as well as others that we're featuring throughout the week, is the formalisms help, because formalisms help to get to a more accurate answer, and you can actually know what you were able to answer and what you have not been able to answer. And that's actually part of the overall approach. So in moving forward, I think this is where I'm going to come clean with the audience. My systems are failing left and right. I know questions are coming, so I will have to rely on my colleagues, James and Jerome. If there's audience questions that we should be addressing, we should pick them up. So I know a couple of those are moving along, but I'm not able to see them. So are there any that came our way that we should address, or we can continue with our plan?
Yeah, so actually there are two regarding my presentation, and one for James, so that will come in shortly. So let me start with probably mine, just to be, because they are the first in the queue. So lessons learned regarding providing feedback into the model derived from testing on real hardware. That question depends really on some ongoing work that is currently being done for some SEI customer. So it's not really something that I can discuss. So feel free to reach out to SEI, to info@SEI if you want to have more details about that. The second question was on FMI simulation that we're using for TwinOps. FMI allows you to combine multiple models of times. However, you have to know in advance whether this composition makes sense. FMI is simply a middleware. It will not solve the semantics issue I was presenting before. Basically, FMI, you can just view it as a gluing technology. So if the semantics is not correct, FMI will not detect it and will not report it.
Okay.
Then, James, there is one question for you that I will read. Is can you move from the model of interactions and change to prediction of performance, of safety, of latency? I mean, basically, does it scale to non-functional attributes?
Well, so that's an interesting question because non-functional attributes or quality attributes span a lot of different concerns. The concerns we're tackling with the NOT are typically things that aren't measured at runtime, like modifiability. The others that Bruce mentions, performance, safety, latency, these tend to be things you would measure more at runtime. And you can think of these as not quite partitioning, but related concerns that actually build on very different models usually. So the semantics in the computational model for your underlying analysis are going to tell you what you can reason about effectively. Our starting point with the refactoring work is to focus on those non-runtime measures. How easy is it to maintain the code, to port the code to a new platform, that sort of thing. And so that lends itself to models that have structural sorts of dependencies and that kind of information, more than information like execution time. It's quite possible to combine these models and add information. And that's one of the things that we're thinking about as future work for refactoring, is to add some notion, for example, of common execution paths so that you can penalize solutions that would add latency to frequently executed paths. But really, I mean, I think this is probably true of all of our work at the SEI. The particular computational models we use for any given model will lend themselves to some kind of analysis. And one of the tricky questions that's been a challenge for years is how do you bridge the gap between different kinds of models so that you can reason consistently across these different domains. And there's a little work that we've done there that's pretty encouraging, but it's a big challenge because computational models go beyond just continuous time, discrete time sorts of things into things that have nothing to do with time.
So I'll actually pick up on that, James, because one of the other kinds of work that we've seen is there's quite some work that focuses on, okay, I'll look into the dependencies of the code base. I will improve them because it will improve my modifiability, maintainability going forward. I think what you presented actually provides a shift in terms of how to approach these kinds of dependency correction or improvements. Can you say a little bit about how search-based algorithms and refactoring and our approach actually helps make that trade-off?
Sure. Yeah, that's an interesting thing. So there's a lot of really good work out there on search-based refactoring that looks to improve general code quality metrics, things like coupling, cohesion, some of the QMoon metrics. There's really a very different starting point from that work and the work that we're doing. The existing work out there in the research really is good at making general improvements, but it's done without any particular kind of lens, any particular motivation that this is the piece of code that I care about. In our work, we started from a very problem-driven or problem-focused solution. That is, a user tells us this is the capability that I want to make or turn into a reusable component. That is essentially a constraint on the problem, but it also focuses the solution as something that's much more immediately practicable to a program office or a contractor or any organization who's really trying to get value out of that software as opposed to scattered changes throughout a code base. Both pieces of work are valuable, but it really comes back to the question of what are you trying to improve and why.
Yeah, focusing the problem into the relevant evolution and improvement, both with model-based engineering as well as search-based refactoring, I think at the heart of the advances that we're trying to go after. With that, maybe I'll ask a general question to you both, and you can take turns. So there's all this automation theme that we've been working on and formalization, but there are definitely open research questions out there in terms of DoD adoption. So what would be the open questions and the most important ones that you think we should be working on in order to move these technologies closer to adoption in the near future? James, you want to get started?
Sure. So honestly, the first questions that I think about aren't technical. So the questions that I think about for a program office is, what are you trying to improve? What's the change you're trying to make? And how can you make that a fairly specific thing so that we can measure for improvement? The second thing that is unfortunately still an issue for some programs because of legacy contracts is access to the data that you need to actually do the analysis, right? In our case, we look at source code. So if a program doesn't have source code, that's a huge, huge barrier. Given those two things, we have research that can move in that direction. And from the research perspective, the things that we need to add are support for the right languages that are used in practice. We know there's a lot of variation in that space. Incorporation of the right semantics. For example, do we add more information about latency to make sure that we refactor in a way that respects not just modifiability, but performance? But really, there's a synergy here between what are the concerns that matter, what's the problem we're trying to solve, what's the information that we need, and do we have the access to it? And given that, there's a lot of good research to build on in terms of the computational models that let us do the appropriate reasoning. But there's still work to do to pull that through.
I do agree that there are technical challenges as well as organizational and adoption challenges. Jerome, is there anything else you want to add to that?
Probably just one. James mentioned the impact on the program offices, and that's especially true for MBE. What we want is do a shift left, which is basically spend more time on modeling activities, on early integration. We really believe in that approach. However, it will change the balance of powers or the balance of budgets between activities. And basically, we have to convince program managers that we want to take more money at the very beginning to improve the system or to do improvement earlier in the system. And we know that it will come at some benefits that we can quantify. But for a particular program manager, it means that eventually we'll have less money for late corrective actions that we want to avoid. Mm-hmm. And this is a big shift. We understand that it is a risk-taking shift for DoD program managers, but we really believe that it is the right shift that we would like to support and to enable through our activities and research.
Mm-hmm. And I think it's the common theme that we have shift left with improved automation and improved formalism so that you understand what is the missing information and what you actually still have to supplement so that you can go through the different tasks accordingly. So I know there are questions coming on, but we're out of time. And I thank you all for your patience as we navigate technology as well as we navigated this platform. But we will see and address the questions offline if we're able to. As I said in the beginning, the presentations will be available for streaming tomorrow on our digital library. We'll give a 5-minute break now, and then our colleague Sam Proctor will be on talking about our work in AADL, and then we'll come back again with Jerome and Sam and have another short panel session. Thank you both, James and Jerome, and thank you all for the audience, and we'll all be back in 5 minutes.